Hello. Right, in this lesson we're going to look at Young's double slit experiment, and what we're going to learn about is how Thomas Young carried out his double slit experiment and what it tells us about the behaviour of light. There's an equation to understand, and then we're going to apply all that to see how you can use this to calculate the wavelength of a light source. So let's do a bit of a starter first. Here's a past A-level question. And you've got a diagram which shows a ripple tank. You've got two dippers, A and B, producing waves which are in phase. So that will tell us that because the two dippers produce ripples of the same wavelength, this is a coherent source. The waves travel out and they meet at various places, including point C. So it tells us the distance from A to C and B to C, and it tells us the wavelength. So here are the questions. The first question, it asks what is meant by interference, and then the second question says state and explain the type of interference occurring at C. Notice those two command words there, state and explain. So you've got to give a reason for that. I want you to think of the answer now, and I'd like you to write something down and pause the video until you've done that, and then check your answers, please. Make sure you understand. Okay, so your sentence to explain what's meant by interference must include the two words superposition and coherent. So interference occurs when you've got a pair of coherent waves. Okay, that means they've got the same wavelength and they've got they're in phase. And superposition is when the two waves combine. Okay. State and explain the type of interference occurring at position C. So to work that out, what you need to know is the difference in path length. And to do that, you compare distance AC with BC, so you subtract one from the other, and that gives us a difference in path length of 4.5 centimetres. Then you compare that difference in path length to the wavelength. Wavelength was 3 centimetres, told us that in the question. 4.5 centimetres is 1.5 times the wavelength. So the interference will be destructive. That is, the two waves will cancel out. And we know that because there is an odd number of half wavelengths difference between AC and BC. Okay, so let's get into what we want to know about Young's double slit experiment. We'll start with a bit of history, starting with this man, Isaac Newton. Isaac Newton is probably the greatest English scientist ever to live, and he occupied a professor post at Cambridge University, which was later also occupied by the late Professor Stephen Hawking, and he moved a lot of areas of science forward, and this quote I've put on the screen there I think says a great deal for how science works, in that even great scientists like Newton have to build upon the ideas and discoveries of the scientists that have gone before them, and that scientific process continues to this day. So his work has been very influential. He worked on laws of motion and gravitation, published that in a book called the Principia, and almost 300 years after he published that book, NASA scientists used his ideas to calculate the amount of thrust the rocket would need, the directions of travel and all this kind of thing to get to the moon. If you're doing A-level maths, you've got Isaac Newton to blame for calculus, and what we're interested in here, he did a lot of work in optics. So he made the first reflecting telescope and separated white light into a spectrum, and did all sorts of other work in optics as well. Newton, however, was convinced that light was composed of particles. So a stream of things called corpuscles, he called them. And of course, was he right or was he not? His ideas stood for some time. We'll fast forward 50 years now to another extremely clever man called Thomas Young, and he lived in a time born towards the end of the 18th century, at a time when science was moving forward quite rapidly, and it was possible for people to have an understanding of all areas of science. Thomas Young was referred to as a polymath because he, quite brilliant, made contributions, significant contributions in lots of different fields. Vision, how human eyes work, light, mechanics, you've already studied Young's modulus, energy, physiology, language, music. But what we're interested in here is about waves. He used a ripple tank to demonstrate the interference of water waves. And then he went on to devise an experiment which he quite modestly said could be carried out using equipment that anyone could have to hand. And he demonstrated that light had wave properties. And that established what became known as the wave theory of light, and that contradicted Newton's ideas. The interesting thing here is, because Young showed that light behaved as a wave, the assumption was that Newton was wrong and it couldn't be a particle. Now, we'll come back to this idea in a later topic, because it turns out they were both right, and that light can behave both as a wave and as a particle. More of that later, but that's not particularly relevant to this lesson. So thinking about interference then, what we studied before was, in order for interference to happen, we need two sources which are coherent. So the two pictures there show ripples on a puddle produced by raindrops. That's not a coherent source. So although you could observe interference, it's not a stable pattern and it disappears. In order for something to be coherent, there's got to be a constant phase difference, and the two waves have to be the same frequency. So the ripple tank, the top picture, is showing interference because the two sources are coherent. The dippers will be the same frequency, and they will have, at any given point, there'll be a constant phase difference between the two sources, which is not true of the puddle because the raindrops arrive with a random frequency, which is obviously then changing. So light, well, we know that white light is a mixture of colours. Newton demonstrated that. So it's much more difficult to get a coherent source of light, that is, where there is a single frequency, because most light sources, like a filament lamp, produce light with a range of different frequencies. Newton and Young, for their light sources, were likely to be using things like candles. Remember, this was before electric appliances were even available. So there'll be different frequencies and a changing phase difference between the two sources, so you can't produce a stable interference pattern that way. So how did Young do it? Well, the first thing was he used a monochromatic filter. So if we were to repeat this experiment today with an electrical lamp, then we could put, say, a green filter in there. That's the colour that Young used. And monochromatic, that means it's producing light of a single wavelength. So that's halfway to it being coherent. The other part is we want a constant phase difference. The two light sources have got to be in step. So what he did was he had a single slit, and because it's a narrow slit, the light spreads or diffracts from that place and reaches S1 and S2, but because the waves that reach S1 and the waves that reach S2 have both come from the same location, the narrow single slit, they'll be always in step. This means now we've got a coherent source. This type of experiment is known as a double path experiment, and it's using that single slit and a filter to make a coherent light source. Today we don't have to do that. We can simplify it a bit, as we'll see later on. So one of the reasons why we would not choose to use this arrangement if we didn't have to is because that diffraction through the narrow slit S means it's quite faint. So you can get a brighter source if you can produce a coherent light source in the start. Right, so what did Young observe? So at the time, remember, it was thought that light behaves as a stream of particles. So here we can recreate the experiment using a stream of particles, using sand. Sand obviously is made up of very small particles, and if you pour them through a pair of slits, what do you get? The grains fall through either the left-hand slit at the top or the right-hand slit at the top, and they fall to the screen at the bottom, and they land in a pile, well, two piles. There's no interference pattern there because those are particles, not waves. So the analogy in this experiment is that the the depth or the amount of sound at any given point is the intensity of the light. We'd see, if this was light behaving as a particle, we'd see two areas of bright light which would gradually fade out to the edges. Incidentally, I stole this photograph from the website of a well-known American physicist called Chad Orzel. He wrote a book called How to Teach Quantum Mechanics to Your Dog, which I thoroughly recommend. It's a very readable book, and it goes through a lot of the physics that you need to know for A-level in a really readable and understandable way. So that's well worth looking up. How to Teach Quantum Mechanics to Your Dog by Chad Orzel. So this is not what we see in Young's experiment. What we see in Young's experiment is a series of coloured stripes or fringes. So here's the diagram out of the book, and you can see on the right hand side I've added a photograph of the kind of thing that you might observe, and what you get is the light from the single slit arrives at the double slits S1 and S2 in phase, and because it's got the colour filter, it's monochromatic, so single wavelength. We've got a coherent light source. In the area where the light from S1 and S2 overlaps, we see this interference pattern. You can see it's brighter in the middle because the intensity of the light is greater, and it fades away to the edges. So this interference pattern formed where S1 and S2 overlap demonstrates that here light is definitely behaving as a wave, and this established what's called the wave nature of light. And we can use these ideas now to do some calculations. There's an important formula that we can derive which helps us to apply this. So look carefully at this diagram. This is quite a lot of steps in understanding this. So on the left hand side we've got the slit, the double slit, S1 and S2, and light travels out from S2 and S1 towards the screen, which is on the right hand side of the diagram. And we've got these two slits. Now in reality they'll be quite close together, probably less than a millimetre, and when you have a double slit usually it's marked on there what the distance between the two slits is, and that distance we'll just call that A for now. So the light travels out from S1 and S2 to reach the screen, and we get this series of bright fringes. The central one, as you saw in the previous slide, is the brightest, so that's at point Y, and then you get a darker patch, and then you get another bright fringe at point X. Okay, now the distance of the screen, it's important that that is very large compared to A. Well, if the distance between S1 and S2A is say a millimetre even, if you've got the screen at a metre away, that's 1,000 millimetres, that's much bigger than A, but it's important that that distance is really large. So this diagram is very much not to scale. If you like, the horizontal scale, the x-axis on this diagram is much bigger than the y-axis, if you like. Okay, so what that means is we can measure the separation between the two fringes, x and y. Okay, now there's another slight thing, isn't there? Can you see that they've used the distance is a lowercase x, and then there's also a point x, but that's a capital letter. So the capital letters on here represent the positions, whereas lowercase letters represent distances. Just bear that in mind. Okay, so point X is a bright point, so that's constructive interference. We get constructive interference where the waves are in step. So point Y in the middle was in step. If we move away to a dark patch and then back to a light patch at X, the difference in the path length from S1 to X and from S2 to X must be equal to one wavelength. So on the diagram there, can you see that there is a point P marked? So the distance from point P to S1 is one wavelength. We know that from the fact that x is a bright point, so the two waves must be in step. Okay, so remember what I said about this diagram not being to scale. Those two rays from S1 and S2 going to X, they're almost parallel. Okay, imagine if A was only a millimetre apart and they're travelling a metre, they're going to be very, very close to being parallel. So that means that the angles θ1 and θ2, oops, I've realised there's a typo on my PowerPoint there. It should say θ1 and θ2, not θ1 and θ1, obviously. So those two angles, θ1 and θ2, they're very small and they're almost the same. So that lets us use a trick of trigonometry, something called the small angle approximation. And what that says is, when an angle is very small, so not far off zero, the sine of θ1 will be the same as the sine of θ2, and that will also be will be almost the same as the tangent of θ2. Okay, so just look at the yellow triangle. That angle there, where between S1P and S2, that angle on that corner there, it's almost 90 degrees. Imagine if you rotated that yellow triangle round. That is in the same proportion as the shaded triangle. That's why sine θ1 and sine θ2 are the same and approximately equal to tan θ2. So we're going to use this small angle approximation. Here it is. So the sine of θ1. So the sine is the opposite over the hypotenuse. The opposite is that distance from S1 to P, and we know that's one wavelength, so that's lambda. And then the hypotenuse of that yellow triangle from S1 to S2, that's distance A. So the sine of θ1 is lambda over A. Right. What about, because we know that the tangent of θ2 is equivalent to the sine of θ2, so tangent is the opposite over the adjacent. So the that means that we've got the opposite, that's x, the distance between the two fringes, and then the adjacent, that's the base of that hatched in triangle, that's d, that's the distance from the double slit to the screen. So if we say that sine θ1 is approximately equal to sine θ2, that means lambda over A is approximately equal to x over d. And that's usually rearranged slightly to make lambda the subject. So lambda is approximately equal to ax over d. Now, the big assumption with this is the equation will only work if A, the separation between the two slits, is much smaller than D, the distance from the screen to the slits. Okay, and provided that's true, you can use that equation to find the wavelength of any wave producing an interference pattern. That could be light, as I hope we'll do in the classroom in due course, or that could be sound. That could be, for example, a pair of speakers connected to the same signal generator. The equation will work for both. So how do we do that? Well, in the modern day situation, we'd use a laser light. Laser light is already coherent, so that it's a single wavelength. This one's a red laser. You get other different colours of laser. Remember, the colour tells you something about the wavelength. Think back to the electromagnetic spectrum. Yes, if it's red in colour, is that short or long wavelength visible light? Could you give me an estimate of the wavelength of that light if it was red? These are things that you should be able to estimate. Anyway, it's coherent. When it arrives at the double slit, then that means single wavelength. The waves are all in step, so the two sets of waves travelling out from each slit will have a constant path difference. And then if you have a screen, you'll project a series of bright fringes or spots onto a screen. So what would we need to measure then to work out the wavelength of the light source? Think about what we just went through there in the previous slides. What would we need to measure? There's the equation we just derived. Well, we need to know the distance between the slits. That's the A of the AX over D. We need to know X, which is the distance between the bright spots or fringes. And then we need to know big D, that's the distance from the slits to the screen. Remember that the distance between the slits must be much smaller than the distance to the screen. Okay, so here's what we might see, a series of these little dots. So to get a more accurate measurement, what we'd actually do is measure the distance between several of the bright fringes. So if we did the distance between, I don't know, 10 fringes and then divided by 10, that would give us a more accurate measure. Okay, good. Right, so what have we covered? We've described Young's double slit experiment. You need to better describe that, and you also need to be able to say how that provides evidence for light behaving as a wave as opposed to as particles. And then there's an equation, lambda equals AX over D. You need to understand what measurements we would need to take to be able to calculate the wavelength, and also the assumptions in that equation. And then finally, you need to be able to apply all this to be able to actually calculate wavelength in a practical situation. So to that end, we'll turn to the textbook. What I'd like you to do, this is all on page 230, I'd like you to answer those questions there, and I'd like you to upload those onto class charts for me, please. When you've done that, I'd like you to do the summary questions, please, from the same page. And again, could I have that ideally in a single document onto class charts? You can either type the answers, please don't type the questions out, type the answers into a Word document and upload that, or you can write it on paper, take a picture and upload the picture as you wish. I'll mark that and I'll provide you feedback on that. If you've got any questions, you can leave them as comments under this video. I've done it so that you will be able to do that this time, or you can obviously send me an email, which of course you can do at any point if you need any help. Best of luck, see you soon, bye.